Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to talk about thermochemistry. We've just finished our discussion with several examples of thermodynamics, discussing energy and heat and work and things like that. So I thought it would be best, instead of discussing thermochemistry theoretically and then doing problems, I think it's best just to do the problems, and then within the problems itself, discuss anything that needs to be discussed theoretically, which is actually very, very little. Much of this is stuff that you already know from general chemistry, just a couple of the problems are a little bit more sophisticated than perhaps what you're used to, except for the first one, which is going to be very basic. So let's jump right on in. Okay, so this one is nice and easy. It says find delta H for the following reaction. We have titanium dioxide plus chlorine gas goes to titanium chloride and oxygen gas. So notice we have solid, gas, solid, gas. Okay, so finding the delta H for the reaction is really, really simple. Again, we know this from general chemistry. Let me see, what color should I use? I think I'm going to do blue because I like blue. So we know that the delta H, well, it's equal to, well, we'll just say the delta H of the reaction, okay? And we remember that this little degree sign up above there represents standard conditions. So standard conditions happen to be 25 degrees Celsius or 298 Kelvin and 1 atmosphere pressure. It's just we need a particular standard, so we choose that standard. Well, it's equal to the sum, boy, I seem to have forgotten how to write with this pen here. The sum of the delta H's of formation for the products minus the sum of the delta H's of formation for the reactants, including coefficients. And again, this is something that we already know from general chemistry. It's just products minus reactants. Whenever you see a standard table of thermochemical data, thermodynamic data, you're going to have the enthalpies of formation listed, you're going to have the standard free energies, and you're going to have the entropies listed. And you can use those tables. You just take the enthalpy of the products, subtract the enthalpy of the reactants, making sure to include the coefficients, and that's it. That gives you the actual enthalpy change for the reaction. The heat of reaction under constant pressure conditions, because again, under constant pressure conditions, the enthalpy is equal to the heat. So let's just go ahead and calculate this. And again, all we need is a table of thermodynamic data. So we have delta H is equal to, now delta H for elements in their standard state is 0. So this is chlorine gas, Cl2, so that's going to be 0, and O2 gas, so that's going to be 0. So we only have to worry about that one and that one right there. So when we look up the enthalpy for the TiCl4, we have minus 803 kilojoules per mole times 1 mole. Okay, so those cancel, and then we add to it the enthalpy for this, which is 0, and then we subtract the sum of the enthalpies of formation for the reactants. We get, for the titanium dioxide, we look it up, at minus 945 kilojoules per mole, and again, the coefficient on that is 1, so it's times 1 mole, and then again, plus 0. So it's going to be minus 803 minus a minus 945. So we have a delta H for this reaction is going to equal 142 kilojoules. That's it, or 142,000 joules. Again, make sure you watch out for the units. It's really, really important. Units, when you're looking at a table of thermodynamic values, the enthalpies of formation and the standard free energies of formation, those are in kilojoules per mole. The entropy is going to be in joules per mole Kelvin. So later on, when we actually get to the equation that you're familiar with, the delta G equals delta H minus T delta S, when you're mixing those up, when you're working with entropy as well as enthalpy and free energy, we want to make sure to make sure the units match. So we either need to convert the enthalpy to joules, or we need to convert the entropy to kilojoules. So just thought I'd let you know. So 142, there you go. That's it. So this is positive enthalpy, which means this is an endothermic reaction. In other words, in order for this reaction to both go forward, it actually has to pull 142 kilojoules of heat from the surroundings. It has to go into the system. That's it.